Hypertext Transfer Protocol, or HTTP, is a method of communicating between computers, usually across a network or over the internet. You probably use it quite a lot when you browse websites. While most embedded systems, like our ESP32, do not support full browsers, HTTP can still be incredibly useful for talking to servers and other computers over the internet. In fact, many IoT servers work with REST, which is a communication model that usually runs on HTTP. Knowing how to use HTTP will help you build REST-based applications and give you a foundation for working with other protocols like MQTT. I'll show you how to make a simple HTTP GET request using sockets in ESP-IDF. Before we do, let's talk about how HTTP works. If you've studied networking, you've probably come across the 7-layer OSI model, which stands for the Open Systems Interconnection Model. It's a helpful way to think about layers of abstraction when working with data transmissions across multiple interconnected networks. But it's honestly not a very accurate model for most internet traffic. The first layer, the physical layer, is made up of all the hardware components like the antenna and transceiver built into the ESP32, along with the electrical signaling either in the air or in the wires. Lucky for us, we don't have to mess with that. Espressif has done all the hard work. Next is the data link layer, which is the lowest software layer, often covered by your network driver. This could be some low-level Wi-Fi library that implements the IEEE 802.11 standard, or maybe 802.3 for Ethernet. It is concerned with point-to-point communication between nodes with specific MAC addresses. Going up, we have the network layer, which handles packet routing. This is where IP addresses come in. Nodes on a network can be assigned different IP addresses, and so the network layer has to figure out how to route packets to different nodes. From there, we have our communication services in the transport layer, like TCP and UDP. Such protocols, especially TCP, ensure the reliability and flow control of messages. Layers 5 and 6 are a little more hazy, as this is where the model somewhat breaks down. While the session layer is meant to manage connections between computers, that task is often taken up by protocols in the application layer these days. Similarly, the presentation layer is supposed to be for software that handles the syntax of the data being transmitted, but most applications now just do that. The application layer has an almost endless array of protocols. The popular ones we'll work with include DHCP, DNS, and HTTP. Encryption schemes like SSL and TLS actually work across multiple layers, which is another reason this model is not very accurate. We'll rely on the ESP-IDF networking libraries to handle most of the lower layers for us, but for this demo, we will need to craft our own HTTP message. Here's an example of such a message. Notice that it's just text. Without any added security, like TLS, HTTP is transmitted in plain text. The first line is the actual request. In this case, we are performing a GET request and specify the HTTP version. Version 1.1 has been around since the late 90s and it's still supported today. You'll sometimes come across versions 2 and 3 supported on servers and clients, and they add some additional features such as improved performance, reliability, and non-text protocols. Next are the headers, which are formatted as key-value pairs. Some are optional and some are required by the particular service you are trying to communicate with. The accept header says that we, the client, will accept any media type. We also tell the server that we can handle data that's been compressed by the deflate or gzip methods. Often you'll see clients identify the browser. In this case, I'm using a Mozilla browser, likely Firefox, and I'm on a Windows computer. We also need to specify the host, which is the name of the server we're requesting data from. In this case, we are making a simple HTTP GET request from example.com, and we are requesting the resource located at the root directory of the server, which is given by the / after GET on the first line. Most servers understand this as requesting the home page, which is usually index.html found in the root directory. If you include a body in your request, which is just some data, you might see some other headers that give information about that body data, like the content type and length. There is always a blank line after the headers to denote the end of the headers, and there is an optional body that could include some data. For example, you might want to upload something to the server. GET requests don't usually include a body, but other request types might. There are a number of HTTP request types. The most common are GET for requesting a resource from a server, POST to send data to a server, often to create a new resource or trigger an event, PUT to update an existing resource, and DELETE to remove a resource. You'll see these types used often in REST-style API requests over HTTP. A socket is a concept in software used to define an endpoint in a two-way communication session. You can have stream sockets that use Transmission Control Protocol, or TCP. These ensure reliable, bidirectional, and ordered data transfers. Datagram sockets, on the other hand, use the User Datagram Protocol, or UDP. These are faster than TCP as they lack the streaming and acknowledging protocols, but delivery and order of the data is not guaranteed. A normal socket connection might look something like this. In most networking situations, you have a client and a server. We're ignoring peer-to-peer for now. Both the client and server would create their respective sockets or endpoints. Note that sockets support either TCP or UDP. You can select which protocol to use when you initialize the socket. Many C-based networking applications use the BSD socket API, and ESP-IDF is no exception. So I'll show those function calls here. The server would then bind its socket to an available port on the computer that can accept incoming requests. It then sets the socket to listen. The client then initiates the communication by calling the connect function with the address of the server. Once the connection is established, bidirectional communication can happen using the send and receive functions. In general, the client will initiate communication first, usually with something like an HTTP GET request. Once either side is finished or some error has occurred, the close function can be called. Usually calling this function notifies the other side that communication is terminated and the socket is closed. That being said, both the client and server should be able to fail gracefully and clean up any necessary resources if communication is broken without a successful close notification from the other side. Let's see how this works in practice on the ESP32. For this demo, you'll just need an ESP32 board. If you don't have one, QEMU will also work, and I'll show you how to enable networking for that later in the video. For our demo HTTP request application, we're going to be building it on top of a network driver. In this case, we will be using this network wrapper that allows us to select between either the Wi-Fi station mode driver that we built in a previous video, or you can select the QEMU Ethernet driver if you want to run stuff without an actual physical board. I will demonstrate how to use that wrapper to switch between either of those drivers in a moment. It will require menu config to do so. That being said, in apps, let's create a new folder. We will create our new project called HTTP request. In there, we will create a main folder, and we will create main.c. At the top, we'll need to include some header files for libraries. In this case, we will need the main string library, ESP event, ESP log, ESP-NetIF for the network interface. We need FreeRTOS in order to do things like delaying our main thread, the non-volatile storage or NVS flash library, and the LWIP, which is something else we need for networking. We will also need the header file for that network wrapper, and that wrapper just provides a common interface so that we can make function calls to establish a network connection using either Wi-Fi on a physical board or QEMU Ethernet. In our main thread, we are going to sleep 5 seconds between iterations of our main super loop. For this very simple demo, we are going to have a static URL and host that we are going to fetch the main web page from. In this case, the host is example.com, and it's listening on port 80, which is the main HTTP port that we can connect to and get our web page from. The URL, or Uniform Resource Locator, tells us which resource from the host we want to fetch. In this case, it's just the root path at the host, so it would be example.com/. By default, that means fetch index.html from that path. So we are just going to get example.com/index.html. When we say we want to fetch /, the server automatically knows we mean index.html. So that's the page we will get by requesting that resource. Now we will construct the main HTTP GET request. This is a very simple string. But the words, the spacing, the new lines are all quite important so that the server knows how to interpret it. We will start the request with get in all capital letters, followed by a space, and then the path to the resource we want. In this case, it's just slash. So get root, and the server will know that we mean slash index.html, space, HTTP and the version. In this case, we are going with version 1.0. This is a very simple request. After that, we need a new line in order to write out our headers. Headers are given by key value pairs. Almost every server is going to require this host header, where we define the host we want to connect to, in this case, example.com. The server is going to verify that, yes, that's the server we are intending to connect to, followed by a colon, and then the port we want to connect to, in this case, 80, and then a new line for the next header. Most servers seem to require this user agent header so that it knows what's trying to connect to it. You could put almost anything here, but some servers do verify that it's some kind of browser, say a version of Chrome or Firefox that's trying to connect in order to respond to it. So in general, it's a good idea to put the user agent header in here. Note that there is a blank new line after the headers. In an HTTP request, you can then fill this out with some sort of data like this. For GET requests, you will almost never see data here. But for something like a POST request, if you're trying to send something to a server, this is where you would fill out that data in order to send it to the server to be interpreted. Say, for example, you're logging something to a website, but we are not going to include our data here for our request. We are just going to do a simple GET request, and the server is going to respond with a resource, in this case, index.html. We're going to define a few timeouts here. The first is for our connection. This is our network connection, whether to the virtual Ethernet or for Wi-Fi. We're going to wait for up to 10 seconds for that connection to happen, be established, and for us to get an IP address. We will also have a socket timeout. This is the amount of time we will wait in order to receive a response once we've established a socket and sent our request. We also want to set a receive buffer size. As we receive data from the website, we are going to just print it to the terminal. We don't know how big this index.html is, and the server is going to send it over in chunks. So all we're going to do is just fill up a buffer and then dump that buffer to the terminal, which allows us to stream the information from the website without having to wait for the entire thing to fill up. You could create a larger buffer, save the entire page, and then print it, but on smaller IoT devices like this, you might not have enough memory to store large, complex web pages. So that's why we are going to stream it to the terminal in chunks of 64 bytes at a time. Then we're going to have a tag for our app so that we can log messages to the console and see where those messages are coming from. Let's go ahead and write our main function for the application. We will need a few variables for this function. We will need the ESP return code, a different return code for sockets because those are different than what we get from ESP-IDF. We want to use this address info struct to store our DNS result when we do a DNS lookup. That information, including the IP address of the server, will be stored in this struct for us. We will want a sock handle, which is usually just an integer. We will create our receive buffer here and give it the receive buffer size as the length of that array. We will have a receive total, so we will know how many total bytes we got from the server. Receive length, which is the amount of bytes we got at a time per chunk. We also want our event group and the bits in that group so that we can monitor the network connection to know when we have connected and gotten an IP address. When we do a DNS lookup, we usually need to provide some information about what we're trying to get out of that DNS lookup. In this case, we will say we either want IPv4 or IPv6. That's what's given by this AI_family field in this struct. Web family is a pound define that we're going to use later. Web family is defined in that network wrapper. This is usually something like AF-INET for IPv4 or AF-INET6 for IPv6. You'll also see AF_unspec for unspecified, meaning use whichever is supported by the server, IPv4 or IPv6. We also have the sock type. Sock stream means we want a streaming socket. This is usually used for TCP connections as opposed to sock dgram for datagrams. This is UDP. So that's how we determine we want to stream the data and which IP version we want to use. Here's where we can set that socket timeout. This is given by the timeval struct. We are going to set it to 5 full seconds and no microseconds to go along with that. We'll print something basic to the terminal so we know everything is working. Then we will initialize our event group so that we can monitor the state of our network connection. Then we will initialize the non-volatile storage. The Wi-Fi driver uses NVS to store various settings. If this comes back as a failure because we're out of free space or there's a new version, go ahead and erase the non-volatile storage and then try to reinitialize. If that fails, we will just print an error to the screen and abort out of the main application. Looks like I need to add a parentheses here. Then we will initialize the TCP/IP network interface. Note that you should only do this once in an application and it needs to be called prior to initializing our main network driver. Just like our network interface, we also need to initialize the default event loop that runs in the background. This is something that comes with ESP-IDF. We just call this function ESP event loop create default. That starts running an event loop in the background that allows us to do event-based programming and allows us to create things like callbacks. The Wi-Fi and QEMU network drivers rely on this background event loop to be running in order to handle those events as per the callbacks. So these are the 3 main functions we must call before initializing our network driver: the NVS flash init, the ESP-NetIF init, and the ESP event loop create default. With those running, we can now fire up our main network driver. With those in place, we will initialize our network connection by calling network init. That's part of the network wrapper. We pass in the event group so that we can monitor the bits in that group to know when we have a connection or we've lost a connection. If that fails, we'll just log something to the console and abort the whole application. If we go into components, go into network wrapper. If we go into network wrapper.c, you can see the network init function right here. And all it does is either call Wi-Fi station init or the Ethernet QEMU init based on which kconfig symbol we have enabled. Let's close out of that. And then we will create our really basic super loop that first ensures we still have a network connection, performs a DNS lookup, does the HTTP GET request, and then prints the response from the server to the console. Now we need to write a little bit of logic to make sure we have a connection and an IP address before continuing. The first thing we'll do is get the network event bits from that event group. We will make sure that we definitely have a network connection, so the connected bit is set. And then we either need IPv4 obtained bit or IPv6 obtained bit to be set. If we're not connected or we don't have an IP address, that means the network connection is not fully established yet. So we will call this wait for network function. We pass in the group that we want to wait for and the amount of time we want to wait. This is another function that the network wrapper handles for us. If we time out or there's some kind of failure, we will print that to the console and we will attempt to reconnect. If the reconnect fails, we know there's a bigger problem, so we log that error and abort out of the whole application. Once we've attempted that reconnect and that seems to be going okay, we will go back to the top of the loop and wait for the connection to fully establish before trying that whole thing again. If we go into network wrapper, you can see this wait for network, and essentially all it does is wait for the connected bit to be set first, followed by waiting for either the IPv4 or IPv6 bits to be set. I see a slight error here, and that is PD true. Actually needs to be PD false. This fourth parameter, when set to true, it says that both bits must be set, in which case we might not get both addresses if you're working with just one IPv4 or IPv6. False says that either one of these bits can be set for this function to return successfully. So we need to set that to false. Let's save that and go back to our main application. Next, we will do the DNS lookup. To do that, we're going to call this very common get address info function. This is part of the BSD socket API that we will use to create sockets, make connections, and read and write from those sockets. We pass in the host. This is the name of the server we want to connect to. The port 80. Those hints we set up earlier so that it knows what kind of information we want from that request. And the struct that is going to be filled out for us. So this is an output struct that's given by this last parameter. If our return code is not 0 for successful, or the result comes back null, that means we had an issue, the lookup failed. We will wait for a second and then go back to the top of the loop to try again. Note that a DNS lookup may give more than one address because servers sometimes have more than one IP address on the internet. That DNS result will come back as a linked list, so we can just iterate through that linked list. We will get a pointer to the address from the first address in that DNS result linked list, and we will go through them one at a time by reassigning the pointer to whatever is in AI next as part of that address struct. If the first address is AFINet, remember this is IPv4, we are just going to print that to the screen. We are going to get the IP address struct from that address struct. We are going to use this inet_n2p function to convert that to a string. That's going to be stored in our receive buffer. That's just a temporary buffer for us. And then we are going to print it to the console. If the IP version or AI family comes back as IPv6 in that particular struct, then we need to treat it a little differently. In this case, we are going to use this separate struct, in6 address, to store that IP address information. We will use the same inet_n2p function to convert the IP address into a string, but note that we have to use AFINet6 and inet6 address string length here as part of those parameters to let it know we want an IPv6 string. As before, we will print it to the terminal, but let the user know this is a v6 address. These iterations will continue so long as AI next does not point to null, which is the end of the linked list. In my experience, and I don't have a great explanation for this, to be perfectly honest, the ESP32 will only give us one address for a DNS lookup. So be aware of that. While this will print multiple, if you get a full linked list back from that DNS lookup, the ESP32 usually just gives us one. So we're going to go with whatever's first in that linked list as the address we want to connect to with our socket. The first thing we do as a client when dealing with sockets is to create a socket. We will call the socket function, pass in the IP address version we want to use. This is given by the DNS result AI family. We then give it the sock type, which just comes from that DNS result, the first DNS result, and then the protocol. The sock type tells us we want to use TCP or UDP. In this case, that should refer to the sock stream that we had set earlier. And the AI protocol also says TCP or UDP. This is usually set to something like 0 so that it's automatically chosen based on the sock type given. If the sock handle comes back as something less than 0, remember this is just an integer, that means there was an error and the socket could not be created. So we will log that error to the console, wait for a second, some arbitrary amount, and then go back to the beginning of our while loop. Error or error number is a global variable that is created as part of the BSD socket API. This is very common in Linux programming, so you should never use this variable name if you're working with sockets. It also provides this string error function that we can pass in the error number, and it looks up a string that corresponds to that error number. So we can print a helpful message to the screen that gives us both the error number and whatever the string says about that error. Next, we will set the socket send timeout. We do this by calling the set socket opt function, give it the socket handle, which is just an integer, and we say we want to set the send timeout using these constants that are defined for us in the socket library. We use our sock timeout struct that we created earlier, and we need to pass in the size of that struct. The return codes are similar to the ESP error codes, but they are a little different. In this case, they're just integers. If they're less than 0, then an error has occurred, and we can use that error or error number to figure out what error has occurred. In this case, if there is an error, we will print that message to the screen, close the socket, wait for some arbitrary amount, and go back to the beginning of the loop. Next, we want to set the receive timeout, which pretty much looks like the exact same thing with a couple of differences. So instead of send, we will do RCV for receive timeout. We will use the same timeout here. You could set a different timeout, but we're going to use the same one. Instead of send, we're going to set the error message to receive timeout that we couldn't set it. Once again, close the socket, delay, and go back to the beginning of the loop if there is some kind of error with that. Then we will connect to the server by calling this connect function. We'll pass it in the socket handle, get the address we got from the DNS lookup, and give it the address length. Remember, this could be IPv4 or IPv6, depending on what that address struct looks like. If there's an error, we'll print that message to the screen, close the socket, wait for a little bit, and go back to the beginning of that loop. Once we have made that connection to the server, we're actually done with the DNS result, so we can free up that struct. And you want to do this to prevent gradual memory leaks. We will call this free address info function, pass it in our DNS result, and let it handle cleaning that up for us. This function is fairly straightforward. We send it a handle to the socket that we have created and set up. This is just an integer. We have the request. This is a string. That is our HTTP request, hopefully properly formatted. We have the length of that string, because C functions want length of strings and arrays, and then any flags. This is set to 0 because there are no flags. This could be things like out of band data or something else, but we're going to keep it simple. Even though this function is fairly simple, all of the setup is required to get to this point, and we needed a connected socket to make it happen. If there is an error, meaning the return code is less than 0, we will print error or error number to the screen and look up the string associated with it. We'll close out the socket, wait a little bit, and go back to the beginning. Let's make sure this waits for about a second instead of 10 seconds and a little bit. If all goes well, the server should respond back with index.html located at the root of that server address or the URL. We are going to print that to the terminal as we receive it in chunks, and we're going to keep a running total of the number of bytes we've received. We'll receive some chunk of data by calling this receive function. We'll pass it in the handle to that socket. We will give it a pointer to our receive buffer and the size of that receive buffer. Notice that we are subtracting 1 from the size of that buffer because we want to make sure that buffer has space for a null character or 0 so that it is a fully properly formatted string that we can print to the terminal. We also won't set any special flags here as well. We will check for any errors. We know this if receive length comes back less than 0, something wrong happened. We will print the error to the console and break out of this loop so that we can close the socket and go back to the top of our super loop. The other thing that can happen is this receive function can return 0. That means we've reached the end of the data, the response from the server, and we should just close the socket and be done with it. We will make sure that there is a null terminator character at the end of the string so that we can successfully print it to the terminal, and we don't have something like a buffer overflow. And then we will increment our receive total variable by the receive length that we got from the receive function so that we can keep a running total of number of bytes received from the server. Now that we are done with the socket, we can go ahead and close it. Just for fun, we will print the total bytes received to the terminal. Finally, we will wait 5 seconds before trying this again, where we will do the DNS lookup, create a socket, connect the socket, send our HTTP request, and print the response to the terminal. We will just continue this forever. Let's save our file and add a couple of supporting files to make this into a full project. Let's bring up a new file. It'll be CMakeLists.txt next to our main.c. In that, we will write IDF component register, so that ESP-IDF knows where to find this. We will give it the location of our source code. In this case, it's just main.c, and any include directories, which there are none for this particular project. Let's save that, and we will create our top-level CMakeLists.txt. In here, we will specify our minimum CMake version, 3.16. We will include that project.cmake that can be found in the ESP-IDF source code. We will append our custom components directory to that extra component DIRs variable that ESP-IDF looks for when it's building our project so it knows where to find our custom libraries. We will also set the project name to app. Let's save that and we can close these down. Let's go to terminal. New terminal, we'll start in workspace. The first thing we will do is set our target to the ESP32 S3. Choose whichever variant you are working with that you have actual hardware of. And I first actually need to go into apps, HTTP request, and run that again. Once that's done, do idf.py menu config. That will bring up menu config, go down to component config. All the way at the bottom, you should see a few options for our custom libraries. We are going to be working with the Wi-Fi station configuration. That is the custom Wi-Fi library that we created in a previous video. Press space to enable that library. You can set the IP version. So if you want IPv4 or IPv6, you can set the minimum security. In this case, I'm going to leave it as WPA2 because that's what my network uses. You will also want to set your SSID string by typing that here and set the password for your network here. If you are working with WPA3, you might need to adjust these options to match the network configuration you have. Press escape. The other thing we need to do is enable this simple network wrapper. Otherwise, our functions won't work because we are using this wrapper on top of our Wi-Fi driver. And in a minute, I'll show you how to switch over to the Ethernet QEMU driver while still using that wrapper. So press space to enable that, Q to exit, Y to save. And now we can type idf.py build in order to build our project. With any luck, this should build, and we will wait just a moment to see what happens. Looks like we have a couple of errors here. As per usual, I forgot a semicolon. Looks like uint32t is a long unsigned int, not just an unsigned int. So we will click on that. I believe LU should work here. Let's try again. All right, that at least helped. I still have a few more errors. I forgot a comma here. All right. And it looks like everything built, which means we are ready to flash. Bring up a terminal on your host computer, navigate into the course directory or the repository directory, activate the Python virtual environment, go into the HTTP request application folder that we've been working in, and go ahead and write out that python-m ESP-tool flashing command. Make sure you give it the correct port for your ESP32 chip. Tell it to auto-detect the type of chip we're using, set the baud rate, reset before and after, do the write flash, set the flash mode to dual I/O, flash frequency to 40 megahertz, auto-detect the flash size, give it the starting addresses of the bootloader, the partition table, and the application. Remember that the address for your bootloader might be different depending on your ESP32 variant. For my S3, this is hex 0. For a base ESP32, this is probably something like hex 1000. With some luck, that will flash, and we can type out python-m serial.tools.miniterm, give it the port location, and the baud rate of 115200. That should connect to your ESP32, which should reset. And with any luck, you should see it connect to your access point. It should print out the SSID for your network. You will see it connect to the network. It should get an IP address from DHCP. Once it's fully connected, it will do a DNS lookup. In this case, it succeeded. Example.com is located at 96.7.128.175. Once that DNS lookup succeeds, it sends out our HTTP GET request. Hopefully the server responds. We should get a response that says the HTTP version it responded with. 200 is the code for OK. We have a few headers here. The content type is text, basic text, HTML. We have some tags, last modified, the date, and so forth. It also gives us the content length, which is useful if you're trying to parse that or know how much to expect. And then we print out the actual HTML we received from the server. If this was a graphical browser, it would display this quite nicely for us. But since this is pure text, we just get the ASCII, or in this case, UTF-8 characters printed in RAW to the console. Here is the end of that HTML, and it prints out the number of total bytes received. In this case, 1,521. Looks like I forgot a new line in that printf here, but it should wait 5 seconds and repeat that entire process again. If you get this page printed out, it means everything is working. You know that you can connect your ESP32 to a network and have access to the outside wider internet. I'm going to minimize this, and I'm going to make that correction right now. So I'm going to add \r\n to insert a new line on that printf. Let's save. If you don't have access to physical hardware, you can also try this with QEMU. In the terminal, make sure you are in the HTTP request folder. Call idf.py set target. I recommend using the basic ESP32 variant. for this, as I have run into issues with the S3 variant in QEMU. So let's set that, wait a moment for that to complete. From there, let's call idf.py menu config. We'll go to our component, scroll all the way down. Notice that everything has been reset. When you call set target, it removes all the previous configuration that we had, as the variants might have unique configurations. We are going to enable that simple network wrapper. Press space there to enable it. Press enter to go into the Ethernet QEMU configuration. Press space to enable that. Feel free to choose which IP version you want. This usually depends on your network support. IPv4 is still in wide use, so I'm going to leave it at that. Press Q to exit, press Y to save. And now we are going to enter idf.py QEMU. And I'm going to go ahead and say monitor so we can get nice, pretty colors for the output. That should automatically build our project and fire up the QEMU emulator for us. Once that's done, you should see the ESP32 reboot. You should see it connect. Hold on, let me scroll back down. I don't know why that jumps up. Seems to be some weird bug in VS Code. So here is the virtual ESP32 rebooting. You see it connect to the virtual network inside the QEMU emulator. It waits for an IP address. It gets 10.0.2.15. Notice here is the gateway. That is the computer outside of the QEMU emulator. In this case, it's the Docker container. You can reach that by default by going to 10.0.2.2 from within the QEMU emulator. That gets you to the host machine, which, remember, in this case is the container, not the full host machine. So we have an emulator inside of a Docker container inside of a host machine. We print out the IPv4 address here that we've obtained. Now that we are fully connected, we can do the DNS lookup. We get the IP address of example.com, and we see the same thing. We have the OK code, and we print the entire HTML to the console. Looks like I keep jumping here, so let me scroll back down. You can see the number of bytes received, and I did include a proper new line here before the process repeats every 5 seconds. Hopefully this helps you get started using sockets and making HTTP requests using ESP-IDF on your ESP32. Understanding how to work with sockets opens a world of possibilities for creating robust networking code at a low level. As you've seen how to make GET requests, you can now also start creating similar requests for REST-style API, which is incredibly popular on the internet. If you enjoyed this video or found it useful, please click the like button. And if you want to learn more about writing firmware for IoT devices, I recommend checking out my online course. We start with the basics of ESP-IDF for writing professional code for the ESP32, then learn how to read from connected sensors and transmit that data over Wi-Fi using HTTP REST API calls to an IoT platform. We'll also tackle publish-subscribe mechanisms with MQTT, before seeing how to secure everything using Transport Layer Security, or TLS. By the end of the course, you'll have the chance to build a full IoT sensor that publishes data to an MQTT broker, and you'll earn a digital certificate to showcase your new skills. Click on the link in the description to sign up.